Welcome to geometry. We want to take a look now at section 19, which is about similarity. This is a topic we haven't seen yet in this course, so we're not referring back to some things that we've already seen. We're taking a look at some new ideas. Not that it's a new idea overall, I suspect you're quite familiar with it already. So, two sequences of non-zero numbers are proportional if, when we take the ratio of each term, first term, second term, and so on, if that ratio is equal to a constant k. Now this k can change, right? It's going to be different for every sequence of numbers. So I might have 1, 2, 3 for my first sequence, and then 2, 4, 6 for my second, right? So 2 divided by 1 is 2, 4 divided by 2 is 2, 6 divided by 3 is 2, so our constant would be 2 in this case. But of course, if I were to take 1, 2, 3, and let's say 5, 10, 15, then of course, when I divide, 5 divided by 1 is 5, 10 divided by 2 is 5, 15 divided by 3 is 5. So k would be equal to 5 in this case. So our k value can change. All right, this k value is called the constant, the proportionality constant. Make sure we get the right words there. No, actually I was right the first time. The constant of proportionality. Excellent. So here's a couple of examples. Of course, another example would be 2, 5, 7 and 6, 15, 21. This sequence is proportional to that one with a constant of proportionality of 3. And it doesn't matter. In both of these cases, right, we're taking the second number and dividing it by the first, whereas the definition says it has to be the first divided by the second. It doesn't matter. It doesn't matter at all. So keep in mind that for different sequences, we're going to have a different k value. And in particular, if we're not working with a specific, right, if we don't have a given pair of sequences, then we're not necessarily talking about a specific k value. Okay? Sometimes we'll have a specific k value. Often we will not. Okay, in the proofs that we work with, sometimes we won't have a k value. The homework exercises, right? You might not have an actual k value. This is a problem that I run across semi-frequently. It's not just an issue with constants of proportionality. It shows up everywhere, right? If I were to talk about even numbers, an even number n can be written as 2k, where k is an integer, right? Depending on what the even number is, changes the value of k. Some of you have already encountered situations where we need to recognize that k can change. Anyway, just keep that in mind. So, it's important to recognize that it takes at least 4 numbers to make a statement of proportionality. Why does it take 4 numbers? Well, because our sequences really should contain at least 2 numbers in each. If I were to not consider any extra numbers, just A1 and B1, if I only had 1 number, then of course I'm going to have it's equal to something. It's going to be equal to something always, right? A1 divided by B1 is always going to be equal to something unless it must be a 0, of course, then it's undefined. But we need to have, in order for us to actually say, hey, there's a pattern here, we need to have a pattern. You can't have a pattern from a single observation, right? What is the pattern of numbers here? 5. There's no pattern, right? It's just the number 5. So similarly, if I wanted to recognize a pattern, that pattern being a constant, I need to have more than just 1 number. So I need to have, right? I need to have more than 1 ratio or proportion. So I need to have 4 numbers, so that way I can come up with 2 ratios or proportions, and then recognize that they are equal to one another, all right? So that is important. All right, so similar polygons. What are similar polygons? Well, two polygons are similar if there is a one-to-one correspondence between their vertices. So if I have a triangle with vertices, a triangle with vertices A, B, and C, if I wanted to say that's similar to triangle D, E, F, I would need to make sure that I have a one-to-one correspondence from the vertices. A goes to D, B goes to E, C goes to F. Okay, one-to-one correspondence. So that the corresponding angles, angle A and angle B, are congruent, and all the side lengths of one polygon are proportional to the corresponding side lengths of the other polygon. So AB is proportional to DE, BC is proportional to EF, CA is proportional to FA, right? And not individually, right? We're talking about the collection A to B, line segment AB, along with line segment BC, along with line segment CA. Those are proportional to line segments DE, EF, and FD, okay? All right, when we have that two objects, two polygons are similar to one another, in this case, triangles, but even if it were a rectangle or a quadrilateral rather, right, we would simply say the object or the polygon is similar to the other polygon. So that is the notation for similar. And we have that, something that you're probably familiar with, right? The polygons are similar to one another if they have what appears to be essentially the same shape, but possibly different sizes. So all of these angles match, but the side lengths don't, but they're similar, okay? Or we take one, right? Triangles, squares, quadrilaterals, whatever the case is. All right, of course, every geometric figure or every polygon is similar to itself with a constant of proportionality of 1. And it doesn't matter which way I say something is symmetric or it is similar. I can, right? Triangle ABC is similar to DEF, but of course we would say that triangle DEF is similar to triangle ABC. So we have symmetry of similarity. And then if we had that triangle DEF was similar to triangle GHI, then we can find a constant of proportionality that would bring us from triangle ABC to triangle GHI. So it's transitive as well. That is to say, similarity is an equivalence relation. So we get the reflexive, symmetric, and transitive, okay? So we'll be able to use that in our homework problems and in proving theorems. All right, so let's take a look at our first theorem, the basic proportionality theorem. Now, based on the notes that I have, you as the student should be able to prove this. Despite us not having any comments about the theorem and no proof provided, right, no comments on the proof, again, you should be able to prove this theorem. So the basic proportionality theorem. In a triangle ABC, so let's take a look at a triangle ABC. We have that DE is parallel to AC if and only if we have one of these equalities here. So what are we talking about? Well, we're talking about, again, is triangle ABC, and we have some line oops, E, say the points of intersection here are D and E. This line is parallel to that line if and only if we have that the side lengths, right, this triangle and this triangle are proportional. So this side length to the overall side length is equal to this side length to this side length, right? That's what this is saying. BD divided by BA, BD divided by BA is equal to BE divided by BC, or BD divided by DA is the same as BE divided by EC, or that BA divided by DA is equal to BC divided by EC. So again, we're just looking at a couple different sequences of side lengths to give us that these two are proportional triangles, essentially. Sorry, similar triangles. All right. So we're going to leave that for now, but this theorem is used for proving our similarity conditions for triangles. And that's what we'll take a look at in the next video. So for now, we'll call it good. And in the next video, so in just a few minutes, I'll see you again to take a look at similarity conditions for triangles.